Welcome to our second part of our lecture in AC power analysis. Today we're going to discuss um, complex power, apparent power, and power factor, the conservation of AC power and power factor correction. So apparent power and power factor is defined as the product of our voltage RMS and our current IRMS, or that is equal to 1/2 of Vm and Im. So it is usually measured in volt ampere or VA. So that is derived from the formula of average power. For power factor or PF, that is the cosine of the phase difference between the voltage and the current. It is also the cosine of the angle of load impedance. So if we have load impedance written in polar form, you have your ZL, and this angle here is can be considered as your power factor. So cosine theta of that is your PF. The power factor may also be regarded as the ratio of the real power dissipated to the apparent power of the load. So your apparent power or power factor is the ratio also of your real power and your apparent power of the load. So we have important uh, concept to be remembered. So if you have theta V, or the angle of your voltage minus the angle of current, is equal to 0, power factor is equal to 1, our load is said to be purely resistive load, meaning that we have here the unity power factor. So it means that all power are consumed in the system. So if your theta B is minus theta I is equal to plus minus 90, it means that our system has purely reactive load, or no average power at all, or no real power consumed in the system. So we have two types of reactive load, either purely inductive or purely capacity. Okay? And for the combination of the reactive and resistive load, we have the difference of voltage angle and current angle can be greater than 0 or less than 0. So when the difference between the angle of voltage and current is greater than 0, it is said to be inductive load, or it is what we call the lagging power factor. It means that our system is inductive and the lags, current I lags voltage, okay? Or the voltage leads current. Now for theta, the difference of theta V and theta I less than 0, it is said to be leading or capacitive load. In this case, our theta I leads the voltage by a certain angle, or the difference between theta V and theta I. So a very stable system should have purely resistive load or has unity power factor. So take for example, calculate the power factor seen by the source and the average power supplied by the source. So first is we need to determine total impedance, the current, okay, the current and the voltage in the system so that we can compute for power factor and the average power supplied by the source. So if we compute for the total impedance as seen by the source, so this total impedance, the angle of total impedance can be considered as your power factor. So in this case, you have series, we have here series elements 8 ohms and minus J6 ohms in parallel with 4 ohms and in series with 10 ohm resistor. So the total impedance gives us 12.69 angle 20.62 degrees. So this angle can be considered also as your power factor in the system. So therefore, the cosine of 20.62 is 0.36 lagging because our system or the angle of our impedance is positive. Okay, so this can be considered as lagging power factor. If we go back to the concept for power factor, so here if it is positive, then our system is inductive. So to compute for the current flowing, since we are concerned with the power, average power by the source, we have the VRMS or the voltage. So this can be simplified as the voltage, and you have here the simplified load or our Z load. Okay, so the current can be computed as V RMS divided by ZL, the impedance, and this gives us a 3.152 angle negative 20.62 degrees. And to compute for the average power, we make use of the formula I squared RMS times R, which gives us 118 watts, or VRMS times IRMS times the power factor or the cosine theta V minus theta I. And this gives us 118 watts. So what is the difference between apparent power and power? What's the main use of power factor in the system? So usually the rating of our load is given in kilowatt. We are familiar with kilowatts, but actually it has to be given in terms of VA. So take for example in this 2 case scenario. So here we have the load, purely resistive load. You have P equals 120 kilowatts and our reactive power is 0. So our load is 120 kilowatts and the generator supplied 120 kilowatt as well. So in this case, the system is not yet overloaded. But as we introduce the reactive power 160 kVAR, so if we compute for the apparent power of that, you have 200 kVA. And if we solve for the current is in terms of S over V. So you have now 200 kVA divided by 600, and that gives us around 300 ampere. But the generator only supply 120 kilowatts of power. So our generator been overloaded. So it is always important to consider power in terms of PA than kilowatt because in a real case scenario, our load consists of reactive power and not just the real power itself. Okay, so next we have here an example for power factor, and here we need to compute for the current flowing in the system. So after the capacitor is being added in the system. So for the circuit in figure, a capacitance with 160 kVAR is added in parallel to the load. So determine now the current I. So we have the inductive load, and to reduce the power factor or to correct the power factor, we have to install some capacitor in parallel with the system. So this is termed as power factor correction. And to do that, we need to compute first for the total power in the system. So the total power of the total reactive power for capacitor is 160 kVAR, and this one, the inductive load, has also 160 kVAR. So we have to subtract the total reactive power by the reactive power of capacitor since this is inductive. So we need to subtract the reactive power of the capacitor. So it will now become 0. So our total real power is 120 watts plus here we don't have real power or average power, so therefore we have 120. The total apparent power is 120 plus 0 kVAR. So thus we have 120 kVA. So to compute for current, we just divide this by the voltage across. So 120 divided by 60 have 200 ampere. Thus, the generator is no longer overloaded. So next, we're going to define the concept for complex power. Complex power contains all the information pertaining to the absorbed by the load. So it is in the formula, or it is denoted by bold letter S. Okay, so you have S equals 1/2 of VI conjugate, which can be formulated also as VRMS times I conjugate or I squared RMS times the impedance, or it can be also written as V squared RMS over Z conjugate. So take note or be careful with the conjugate sign of the impedance. So therefore, in this complex power, it consists of the real part and the imaginary part of S. So the real part of S is your real power denoted by P, and we also have reactive power denoted by Q. Okay, so this real power or the real part is determined using the cosine. P is just S cosine of theta, and your Q is determined as S sine of theta, where theta is the difference between the voltage angle and the current angle. Okay, real power is the only useful power delivered to the load. Okay, and reactive power represent the energy exchange between the source and the active part of the load. So this reactive power is required for reactive loads like motors and other forms of inductive load. Okay, so the unit of Q is var. For P, that is in terms of watts. So S is in terms of VA. So this is the other equation for P and Q. Have P is equivalent to I squared RMS R, and for Q you have reactive or the reactance. Okay, so and we have three types of circuit. We have resistive circuit, we have the inductive circuit, and capacitive circuit. So for resistive circuit, the difference of theta V, the angle between theta V and theta I is equal to 0, and that has unity power factor, or they are in phase. So this is the graph for the voltage, this is the graph for the current, and this is the power of the resistive load circuit. The other one is the inductive circuit. So take note, for inductive circuit, you have theta V minus theta I is equivalent to purely inductive circuit, you have plus 90 degrees. So for capacitive, you have theta V minus theta I equals minus 90 degrees. Okay, so this is for purely inductive and resistive. So they are out of phase by 90 degrees. So the graph for the voltage, have the current here, they are out of phase by 90 degrees. So this is for, um, by the way, for inductive load, we have here the voltage or the current lags voltage by 90 degrees. For capacitive circuit, current leads now the voltage by 90 degrees. So in summary, complex power, we have now the formula. For complex power, it is denoted by the bold letter S. For apparent power, that's the real or the absolute value for S. So this is the formula for apparent power. And for complex power, so real power is just the cosine of S, and for reactive power, that's the sine of S. Power factor is the ratio of between real and apparent power. So for power triangle, this is very important, especially when we determine the required reactive power or the required capacitance or inductance in the system in order to bring back the power factor up to the unity power factor. So unity power factor is in the real part of the graph. Okay, so you have here your current and you have here also your voltage. So they are in phase and has zero degree difference. Okay, so for increasing Q, have lagging power factor. So this is for inductive load. And for decreasing Q, uh, we have leading power factor. This is acquainted to the capacitor, or you have capacitive circuit, and this is for inductive circuit. Okay, for Q equals 0, you have resistive load or unity power factor. So here the power triangle has constant power. Only Q will be changed during the determining for the required capacitor or inductor in the circuit. So again, this is the graph for resistive load. The voltage and current are in phase, meaning they have zero difference of angle. For inductive load, the volt or the voltage leads the current by a certain angle. It depends on the difference between theta V and theta I. For purely inductive, this is 90 degrees positive. For capacitive, you have minus. So this difference is the power flowing back and forth into the system. So take for example, you have the 60 ohm resistor absorb 240 watts of average power, and calculate V and the complex power of each branch. What is also the total complex power in the system? So total complex power of the system is either the power or the complex power supplied by the source, or the total power consumed by the load or by the system. So here we need to determine first for the current as well as for voltages in order to find the individual uh, power or complex power in the system. So we can start by determining the current flowing into this branch, since 60 ohms resistor absorb 240 watts, so therefore we can determine for the current. Let's denote this as I2. This one here is I1. So the formula for the resistive load, you have I squared R, and here we can determine the value for I2. For the resistor, you have 240 watts divided by 60, so we have 2 ampere RMS. So therefore our VO can be determined also here, since we have now the current and the value for the impedance. We have the VO is I2 times 60 plus J2, the impedance. So we have here the VO, and this VO is in parallel with this branch, okay, in this branch. Therefore we can also determine for the value I1, since the voltage is the same with or in parallel with this branch. So VO now, or I1 is VO divided by this entire impedance of this branch. So we have now the value for I1. And to compute for V, just simply uh, reduce this further into simple circuit. We have now I. So I here is, this is your, this is parallel, this is VO. So I here is the total current flowing into that individual branches. So we have I is I1 plus I2. So therefore, our V can be solved using KVL. You have 20I plus VO. So we have V is equivalent to 240 angle 21.45 RMS. Okay, so the power now can be computed as the total power is can be computed as V times I conjugate. So you have 240 times I is this one, so the conjugate of that. So this is now the total power in the system. Or you can also do that by solving first for the individual complex power for each branches, and you simply add that complex power and you will arrive in this answer. So another problem is we have two loads connected in parallel. Load 1 has 2 kilowatts and it has power factor of 0.75 leading. Load 2 has 4 kilowatt and this has 0.95 lagging. Um, Here you have 2 kilowatt, 0.75 leading. So the question is calculate the power factor of two loads and the complex power supplied by the source. So the source is connected also in parallel. So what is the power factor of the system? So here we need to determine the individual S of the system. So you have your complex power S1 and complex power of S2. To compute for S1, we need to have the P1 and the Q1. So since the given is 2 kilowatts and 0.75 leading power factor, so we have to determine for the Q or the reactive power, and to do that we need to compute first for S because Q is S sine of theta. So theta is given, so we need to compute for S. S can be found as S is equivalent to P cosine of theta. So P is given, theta is given. We can now solve for S value. So if we do the substitution, we can now have the value for S now is 200 minus J 176.85. So leading. Take note also that when you convert your power factor angle, you have to take note of this term, the leading or lagging. So for load 2, the same principle that we can apply. So take note of the angle. Okay. So lagging, so therefore it should be positive. So our S2 now is 4,000 plus J1314.4 and it is also lagging. So if we add the two complex power, we have now 6 minus 0.4495 kVA. So the power factor can be solved as the ratio of P. In this case, you have this P and the equivalent S for. Okay. So determine first the equivalent apparent power or the absolute value for apparent power. X minus 0.4495 I equals, then we'll convert that to polar form. So you have 6.01. Okay, so in kVA. So we have now 0.95 leading. Leading because the sign of your reactive power, in this case, the sign of reactive power is negative. So this is the reactive part. So next we have the conservation of power. So complex, both real and reactive power of sources equal the respective sum of the complex of the individual loads. So this can be either in parallel or in series form. Okay, so take note always that complex power or S total is the sum of the individual complex power of each element in the circuit. So for example, you have these three loads connected in parallel. So we're going to determine the total power in the circuit. So we need to compute for the individual S power of each element. So we can sum up all the individual complex power. We can say that power is conserved in the system. Okay, so next we have power factor correction. Power factor correction is very important since the smaller the net current or net apparent power, the smaller the current drawn from the supply, meaning we need to reduce from the equation. You have the real power plus J and the reactive power. So the net apparent power should be reduced in order to reduce the current drawn from the supply in the system. So as much as possible, our S should be equal to P or real power, and Q should be equal to 0. We have to reduce this one. We need to introduce some element in the system like capacitor and inductor in order to correct our power factor. So we always bring the system up to the unity power factor. So the process of introducing reactive elements to bring the power factor closer to the unity is called power factor correction. So since most loads are inductive, the process normally involves introducing elements with capacitive terminal characteristics, okay, in order to improve the power factor. So take for example, our system has inductive load, and in order to bring this one up to the unity power factor, so we have to introduce or install capacitor in parallel with that system. So increasing the power factor without altering the voltage or current is called power factor correction. If we graph the voltage versus the current of the original inductive load, so we have here the theta 1, and if we introduce or install some capacitor in parallel with the system, so we can bring back the current up to, or we can reduce the angle between V and I. For unity power factor, it must be theta V minus theta I should be equal to 0. But this one is very impossible in a real power system. So we also have for power triangle power factor correction. So initially you have Q1. So if you introduce some capacitor, so you can reduce this reactive power into Q2. So the difference of this is the reactive or the required reactive power of a capacitive element. So this is the required power in order for you to reduce this amount of reactive power in the system. And from that figure, we can formulate some equation. So for for the reactive power of capacitor, you have Q1 minus Q2. And this Q1 is actually determined using the function tangent theta is equal to opposite over adjacent. And our opposite is your Q1, your adjacent is your power. Therefore, our Q1 is P tangent theta 1. Okay, the same for theta 2 or Q2. Or Q1 also can be solved using the formula S1 times sine of theta 1. Okay, you have Q1, we have sine theta equals opposite over hypotenuse. So our opposite here is your Q1 divided by the S1 or the hypotenuse. So you have sine theta. So from that you have Q1 is sine theta I. So to determine for the capacitor or the required capacitance, so you have to compute first for your QC using this formula, and you have now over I think this is omega v squared RMS. Okay, so this is now the final formula for determining the required capacitor in the system. So power factor correction is necessary for economic reason. Okay, most of the electric cooperative buy power from the generation company. So from generation to transmission to electric cooperative. Okay, so this buy power, this transmission sector or the NGCP buy power from the energy producer company, and this electric cooperative also buy power from transmission or from NGCP, the real power and the reactive power. So if you can reduce this reactive part, you have to pay only the real power in the system. Okay, the same with inductance. So if your system becomes capacitive, but this is very impossible to happen. So if your system becomes capacitive, you can also install some inductor in order to correct your power factor. So the formula for that is V RMS squared and over omega QL. Take note of the difference between capacitor and inductor, since here you have XC is actually 1 over omega C. Therefore, your Q is V squared over XC. That's why you have V squared over omega or omega C V squared. For inductor, you have XL, you have omega L. Okay, so therefore your QL is V squared over omega L. So L is V squared over omega QL. Okay, so take for example an industrial client is charged a penalty if the plant factor drops below 0.85. The equivalent plant loads are shown in figure. The frequency is 60 Hz. So you have the plant load consists of light load and electric furnace, motor loads. Okay, so determine for the total power and reactive power consumed by the load or supplied in the system. So we need to compute for the individual S power of the system. So you have S1, S2, S1, S2, and S3. So for S1, we need to determine for P and Q. Okay. So P is already given. Q for load, lighting load, you have 0 Q bar since this is a resistive load. For furnace, you have the current flowing at your electric furnace is 150 ampere. So you have 54 kilowatts. For Q, you have the reactive or the reactance is 3.2. So you have 72 kbar. For motors, you need to compute for the Q since the real power is already given. Q can be computed using this power factor. So you have P tangent theta according to the triangle. You have here S. Okay, so this is given. So you can apply tangent theta. So this is your Q. So therefore, the total power is you have P1 and P2, 12, 54, and 80. So you have 146. The total reactive power is 0, 72, and 60. So next, what value of capacitance required to bring the power factor up to 0.85. So from here, answer, you have to determine for the power factor. And from that, you have to differentiate. You have to determine the difference of power factor. So here we have power factor equivalent to 42, 42.1 degrees, okay, based on Q total and P total. To bring back the power factor up to 0.85, so we have cosine inverse of 0.85 is 31.8 degrees. Always remember that power is constant in a power triangle. So therefore, we can solve for the new reactive power. Okay, and this new reactive power, from that we can solve for the QC. QC is the difference, the initial Q1 minus your Q2. So our initial Q1 is this one, our Q2 is this, and if we subtract that one, we have, I think, 41.5 kVAR. So this should be negative since we are installing capacitor in the system. Okay, so from this value, we can determine for the required capacitance in the system. Okay, so you have, again, you have QC is equal to QC is equivalent to omega C V squared. So the voltage is equivalent to 600 volts. equivalent to 600 volts. So just divide this by V squared and we can determine now. So you can either use this formula or you derive the XC, then determine for the required capacitance in the circuit. So the required capacitor is 306 microfarad. So for the current before and after, so before the current is determined as 328 ampere, and from the corrected circuit you have 286 ampere. So another problem, we have to find the value of capacitance needed to correct a load of 140 kVAR at 0.85 lagging power factor to unity power factor. It means that for unity power factor, this must be equal to 1. Okay, or theta should be 0 degrees. So from 0.85 to 1. Okay. So the load is supplied by 110 volts RMS, 60 hertz line. So you need to determine the power, the angle of the system. So here we have the angle is 31 point, we convert 0.85, you have 31.79 degrees. So to compute for S, you have given Q, which is 140 kVAR, equal to S equals S sine theta. So here we can determine for the S value. So from this S, we can now compute for P, where P is S times cosine theta. So this gives us 225.93 kilowatts. So to bring our system into unity power factor, we must have resolved the Q, the required Q, since P at original is equal to the P for the system. So we can now compute for the new S, which is the same with the angle of, or the value of the real power. So Q1 therefore is should be equal to 0. Sine 90 or sine 0 is 0. So from that we make use of the formula and we can now solve for the required capacitance of the system. So the application for that is by making use of wattmeter. So wattmeter is the instrument for measuring the average power. So usually we install that one in this circuit diagram. So the current coil of our wattmeter is connected in series, while the voltage coil should be connected in parallel to that terminal. Okay, so this is the formula, average power. So for example, you have here two load connected in parallel. Find the power factor after parallel combination. So before you can do that, you have to determine again the apparent power for individual loads so that you can determine for the total power in the system. So since the given for load 1 is P and power factor, we can compute for Q and S. So S is equivalent to 24 divided by 0.8. For Q from that given, so Q can be determined as 18 kVAR. So this is our S1. So for load 2, you have S2 is 40 divided by 0.95. So you have 42.2 kVA. Q2 is this one. So therefore, our S2 is 40 plus 13.144. So since both load are lagging, this one is positive. So therefore, the total power is 64. 24, you have 64 plus 18 plus this one, you have an 11, it's 31.144. So this is now the S total of our circuit. So to find for power factor, we use the power triangle. You have 64 and 31.144. So theta can be computed as tangent inverse of opposite. You have 31.144 divided by 64. Okay, so theta here is we have tangent inverse of 31.144 all over 64. So 25.95. So cosine of answer is 0.89. So 0.899. This is your power factor. So calculate also the required capacitance in the circuit. Okay, so since we have value of capacitance to raise the power factor to unity, therefore we are bringing the theta to 0 degree since we need to raise it to unity power factor. So from 25 degree to 0 degree, so we can make use of the formula for QC. You have P tangent theta 2 minus theta 1. So you have the value for QC, and applying the formula for C, we can now, this gives us 5.74 millifarad. So here we need to find the wattmeter reading of the average power from the source. So to compute for the, to determine for wattmeter reading, we need to compute for I. We need also to determine the voltage across this area. Okay, so to do that, we need to simplify this one. You have J9 in parallel with 12 and in series now with 4 ohms and 2 ohms. So you have here your total impedance. After determining the total impedance, we need to apply the formula for S power. So you have V squared 120 divided by the conjugate of the impedance. Here is the conjugate. So we have now the S value for, or the complex power of the system. So the wattmeter reading is the average power. So we should take the cosine of S, and that gives us our real power or the average power of the system.